No. Welcome back. Today we do some different study. Rather Android, let's do a little bit PLC because that'll be useful at the day job. Let's go. Allen Bradley PLC control logics and compound logics controller. When create a thing, choose actually the controller you bought. Digital. Close a filter. Add a logic. troubleshooting. Truth is a key element. Examine if closed. Examine the open and energize. And do Wilson, welcome back. Yeah, you're the latest follower actually. After cellist. Only often not allowing power to flow through. Yeah, but turn on like just a push button allows power to flow to that here. But activating XIC, examine if closed, then activated, then power starts going from left to right. If the XIO examine if open, it's activated. Power. It was originally going from left to right, now it's interrupted. No more power. The output energized to use the program store and actually turn stuff on. Timer and condition.
Hey there, it's Stephen Gates here from myplctraining.com, and I've got another video for you today to help you become a confident PLC programmer. And today's video is all about ladder logic. So if you want to learn PLCs, you got to learn ladder logic. So here I have a program, a basic program open with some ladder logic instructions, and we're going to walk through it, and we'll just explain what's going on these 5 rungs. Very simple program, but if you're new to ladder logic, then this might actually seem kind of intimidating. But don't worry, I'm going to walk you through each rung and we'll show you how all this works. So first, just want to make a few comments about the project I have set up here. Notice this is Studio 5000 Logix Designer, and the project is set up for a emulate controller, which is, instead of using a PLC, we have this software here. I'll drag it over, which is Logix Emulate. You can see it's supposed to look like a PLC rack, and we've got a controller there. So then next we have a IB16 in the project, which is a discrete input module for 24 volts DC. And then we have an OB16E output module in slot 2, which is a discrete 24 volt DC output module. Okay, so next let's jump right into the ladder logic. So starting with rung 0, here we have a simple rung with a few XICs. These are XICs, and these function like normally open contacts, if you're familiar with electrical relays, electromechanical relays that have normally open contacts. And we got one XIO here, which functions like a normally open contact. And then we have one OTE, which functions like a relay coil. So notice how the start PB, PB stands for push button, has an address underneath the actual tag name. So start PB is the tag name, and then we have this address under here. And this is called an alias, and basically it addresses one of the points from this input module. So that whenever that point turns on, that input turns on, we turn on tag start PB. So just real quick, the syntax for this, it says local, so that means the local rack, which would be the same rack that the controller is in. And then we have 1, which would be slot 1, that's this guy. And then we have I for input dot data dot 0. So this would be the 0th input, if you will, the very first input available on that module. Next, we have the stop PB tag in a XIC, which is addressed to slot 1, channel 1, or input 1. By the way, these addresses are set up, again, using tag aliasing, which basically means you give the address an alias or tag name, which is more descriptive and convenient to work with. So if you're interested in learning more about aliasing, check out our free training on tag aliasing. It's linked below. You can check that out. And then all the way on the right, we have this OTE instruction. So this is for motor start relay tag, address to slot 2, output 0, so slot 2 is here, and then since it's an output module, we've got an O for output, and then .data.0 for the 0th output. Now let's come back here to the left side again. This is what is called a seal-in or latching ladder circuit. So this part of the logic won't engage until we first engage the output with the upper part of the circuit. So this part of the circuit becomes true. It turns on the motor start relay, which I'll just toggle these just to show you what that would look like. It would toggle that, and then you can see that automatically turns on the motor start relay. So then, even when we turn this off, the start PB, we have a path all the way to the motor start relay. Now, this next item here will be in charge of stopping the motor or interrupting the circuit. And this is an XIO, which again functions like a normally closed contact. And when this tag, the motor running stop timer.done, becomes true, this instruction will open like a normally closed contact would, and it will interrupt the circuit or break the seal such that to start the motor again, you'd have to press the start button again. So if we just toggle that, that would turn this off. Now, one last thing about this rung that I want to talk about here is the stop push button. So here's two questions to consider about the stop push button. First is, why is the stop push button up here rather than here like the motor running stop timer.done? And then second, why is it an XIC instead of an XIO like this one? So for the first question, why is it in the middle of the rung rather than just the seal in or latch in area? Well, having the stop push button here allows it to not only interrupt the seal in circuit path, in other words this path, but it also prevents us from starting it in the first place if the stop push button is pressed. Okay, so the other question is, why did I use a normally open contact or an XIC here? And this has to do with how the stop push button contact is wired to the input module. Now obviously this contact needs to be closed in order to allow the motor to start in the first place. So first I'll tell you why it needs to be like this, and then I'll tell you how this contact needs to be wired to the input module. So here's why. One of the concepts that we have developed in industrial controls over the years is the idea of making a circuit fail-safe. So in other words, designing your controls in such a way that if a control circuit or device or battery source fails, that the equipment that it controls will shut down rather than keep running without a way to shut down, because that's not a good situation. So what we want for our stop button control is that the wires or the push button fails for some reason, or a wire becomes loose and loses connection. We don't want this logic, or we do want this logic to shut off the motor. We don't want it to keep running. And that's for two reasons. The primary reason is that we don't want to lose our stop control of the motor, because it may need to be stopped for safety purposes, and we don't want to lose the ability to stop it. And the second related reason is that we wouldn't know it failed until we tried shutting down the motor if it wasn't wired in a fail-safe way. Okay, so that's why it's important for the stop button to be wired in a fail-safe way. We need the ability to shut it down when the time comes. So what exactly is the correct way to wire it to the input? So how do we wire the stop push button to the input? I'm not going to go into a lot of detail, but it's pretty simple really. We just want to make sure it's a normally closed contact to the PLC. So in other words, when the button is not pushed, we have a true input, so that this XIC will be closed like this and allow the motor start relay to be activated. So that means that if a wire fails or the push button fails for some reason, and the circuit is interrupted to the input module, that will drop this out, and this will become false like that. Okay, so that was a nice little tangent, but I did want you to be aware of the importance of fail-safe circuits like this and how they interact with your PLC logic. There's more to be said about. Okay, so that was a nice little tangent, but I did want true input, so that this XIC will be closed like this and allow the motor start relay to be activated. So that means that if a wire fails or the push button fails for some reason, and the circuit is interrupted to the input module, that will drop this out, and this will become false like that. Okay, so that was a nice little tangent, but I did want you to be aware of the importance of fail-safe circuits like this and how they interact with your PLC logic. There's more to be said about that, but there's a brief introduction for you. So moving on to the next rung, these ones are pretty simple. Basically, we use this motor running input, which comes from slot 1, input 5, and we are either turning on the motor running light or we're turning on the motor stopped light. So this motor running input would be something that is triggered once it sees the motor running at a certain speed. So it could be some relay that detects the motor has reached 1,000 RPMs or whatever the speed needs to be. Or it could be coming from a VFD or something like that. So if motor running is on, then this light will turn on. And obviously this logic isn't running, so it's not responding to the changes in my tags here. And if motor running is off, then the motor stopped light would be on. Alright, moving on to the next rung, let's quickly discuss timers and counters. We won't go into too much detail here for the sake of time, but if you need to learn timers and counters well and get some practice programming with them, you should definitely join our PLC membership called My PLC Training Academy. We go into plenty of detail there. Okay, so rung 3, we've got our motor running input, again, starting a TON timer, which means it turns on when the input is true. And it's set for 30,000, which is 30,000 milliseconds, or 30 seconds. So after the motor has run for 30 seconds, this done bit will become true, which will make this XIC open and interrupt the motor start relay, as we discussed before. So next we have a motor running bit driving the motor run counter. And this is pretty simple. It's a count up counter. So anytime this pulses on, so it goes from off to on, this is going to count up 1. And once it gets to 100, that's going to turn on the done bit for the counter, which will turn on a motor maintenance light. So this would be a situation where the motor's run 100 times, and every time it's run 100 times, you want to make sure you do a maintenance check on it or something. So what's also going on with this rung here is that we're going to turn on the motor run count RES instruction, which will reset this back to 0. So this is another latch-in circuit that will latch in when this goes done, and then when this turns off, because the reset has reset this back to 0, this will stay latched in until the maintenance reset push button is pressed. Okay? Okay, now before we wrap up this lesson, let's simulate starting the motor one time and just see how it works here in the logic. Okay, so here we are online with the Logic's emulate controller, and this little guy just woke up, so he's going to join me on this final part of the lesson. And so I'm just going to toggle this start push button, and I have some really simple simulation logic that basically says if we turn on the motor start relay, wait a couple seconds, and then turn on the motor running input to show that the motor actually started. So let's see if that works. I'll toggle on the start push button. Okay, first of all, we got to make sure our start push button is ready to go, or our stop push button. And then I'll toggle on the start push button, Control T, toggle it off, motor is running. If we go down to rung 3, we can see this timer is timing, and we'll let it get all the way to 30 seconds. Okay, so I realized that the motor start relay and motor running bits were toggling on and off super fast, even though we couldn't see it. And the reason is it was trying to read from this input module, and since there's nothing hooked up to the input module, it was reading a 0, and we were telling it to be a 1 in the simulation logic, so there was a conflict there. So to solve that, I just briefly showed it to you, but open it up here again. Go to the module properties for the input module, inhibit the module, and then it won't be trying to overwrite. So there's a little tip for you, bonus tip. And so when we start this, Control T, toggle it on, motor running turns on, and then you can see the timer start counting here. We're at 5 seconds, and you can actually see this motor run count went to 35 because of that bit toggling on and off. I'm just going to set it back to 0. We'll see it count up to 1 once we restart the motor. So once this reaches 30, it should interrupt the circuit here. There we go. Interrupted the circuit, and of course the motor run count is back to 0 because I set it to 0. If we toggle this on one more time, we'll see this go up to 1. There you go. Okay, so that's it for this walkthrough video of ladder logic. Hopefully you learned something and are just that much closer to becoming a confident PLC programmer. If you're really serious about speeding up the process towards becoming a confident PLC programmer, then definitely check out our membership. It's called My PLC Training Academy. There's a link below, and we'll give you step-by-step courses to become confident with Allen Bradley PLC programming, troubleshooting, and really soon we're adding some training on HMI design to the membership. So that's it for now. We'll see you in the next video.
As owner of Mint Mobile, I wanted to introduce our new family plan with a beloved
latch switch temporarily. Oh. This latch turns it on once, then this is reading its state. Examines the output state, so turns it on first time. How do you turn it off? Or close. It's open. And it right in front of the motor actually. Read the program. Watching.